Yeah, so good afternoon, everybody. Thank you for staying for the last talk of the event. So I'll be talking about the spatiotemporal profile of entanglement in many body localized systems. And this work has been done jointly with Titadi and Bikram and is available on archive in the preprint form. So I'll start by talking in. This is not. Yeah, so I'll start by talking in brief about many body localized systems in the context of many body quantum systems, which exhibit characteristics like absence of transport, which is localized within some short length scale. These systems, as a result, do not thermalize after a global quench, in the sense that if you prepare the system in a non-equilibrium state, they don't evolve into an equilibrium distribution. They have other characteristics include area law entangled eigenstates and logarithmic in time growth of bipartite entanglement, which is in contrast to thermalizing or chaotic systems, which show a linear growth in bipartite entanglement. So normal question to pose in the setting of many body quantum system is that of information propagation, of how does information propagate through space and time. So this can be posed in this manner. So you consider 2 degrees of freedom separated by a distance L, and you ask how long does it take for quantum correlations to develop between these 2 degrees of freedom, or how long does it take for the degrees of freedom to get entangled. And in chaotic systems or systems which do thermalize, one normally looks at operator spreading, one looks at an operator which is initially localized at some site, and one evolves the operator and looks at how the support of the operator grows, which gives a kind of a velocity bound on the operator. So this can be proved by looking at objects like out of time order correlators, which have a velocity bound, which is called a butterfly velocity. So this kind of gives gives a kind of a light cone picture of this information propagation. In many body localized systems, the velocity bound is known to be logarithmic, in the sense that the time it takes for these 2 degrees of freedom to get entangled or to develop correlations will scale exponentially with the distance. So this is what we call the logarithmic light cone. There is evidence for this phenomena using which can be derived through a phenomenological theory of many body localized systems, which is called the L-bit picture. Or there have been numerical studies of out-of-time order correlators in many body localized systems, which also exhibit this logarithmic light cone. However, out-of-time order correlators are not in general a very good pro for MBL, because in MBL you have local conserved quantities, and if you look at an operator which has very high overlap with a local conserved quantity, the operator will not spread. And you can look at the picture where Huang and all probed operators which had large overlap with local conserved quantities, and the profile of the OTOC is very different for two operators. So in this regard, we asked 2 questions. First, what is a good probe of the spatiotemporal spread? And can we develop a microscopic theory based on the probe? So this question will be answered in 2 parts. So we look at the operator entanglement entropy of the time evolution operator as a probe and motivate it as a probe. And this can be related in turn to eigenstate correlations, which I think Bikram talked about before lunch. So the eigenstate correlators will provide us with a microscopic understanding of this. So I'll start by defining the operator entanglement entropy. So you consider the time evolution operator in some local tensor product basis, and you map it onto a state in the doubled Hilbert space. So you just turn the bra into a ket, and this is now a normalized state in the doubled Hilbert space. So this can be imagined in this manner. You can consider folding the operator onto itself, and you can imagine all the legs as being degrees of freedom in some doubled Hilbert space. So what we claim is that the distribution of entanglement in this operator state contains the information about the spatiotemporal profile of information scrambling. So this will be made more concrete in a while. So we will look at purity, which is related to the second Renyi entropy. Purity is a quantifier of entanglement. So we can do all this in the eigenbasis of the time evolution operator, where alpha denotes an eigenvector, and it can be written down like this. We obtain these objects which are denoted by script V, which we call eigenstate correlations. They have contributions from a quartet or 4 eigenstates, which can be written down in this manner. Bikram talked in depth about this in the morning, so I'll just skim over this. So eigenstate correlators allow us to relate this quantity, the operator entanglement, to out of time order correlators which spread from subsystem X to subsystem Y, which are defined like this. So here we are looking at the entanglement across this cut, which is parameterized by this small L. So this relation to OTOX kind of makes it makes this relation quantitative, and we can see that this manifestly captures all the OTOX automatically and is thus independent of what specific operator we decide to look at. So we will first study this setup numerically on a many-body localized system. We use the model proposed by Zhang and Party. So this model is a Floquet model in the sense it has a periodic Hamiltonian, and we look at it stroboscopically, like we look at it after every time period. So the unitary evolution operator after every time period can be written down like this. And for these set of parameters, the system is known to be in the many-body localized regime for a small enough gamma, which the value they quote is 0.3. Looking at the operator entanglement as a function of the cut and as a function of time, we reveal the logarithmic Lightcone. And yeah, so looking at this data in a slightly different manner, we can see the behavior is as follows. The operator entanglement, once you fix the cut and evolve the look at the operator entanglement as a function of time, the entanglement stays constant for some characteristic time, and after which it shows the universal logarithmic growth, which is known in MBL. So this time scale is a function of the cut and is scales exponentially with L, where you have some length scales, which we call zeta. So this scaling of this time scale exponentially is what makes a Lightcone logarithmic. In this regard, we asked the question that how do we explain this in terms of eigenstate correlators, or is there some way we can account for this length scale zeta microscopically? So going back to the expression of operator purity in terms of eigenstate correlations, and which can be written down like this. And here is where many-body localization comes in. Since these eigenstates are eigenstates of a many-body localized system, they are localized in some local tensor product basis. And we leverage that fact to write down the eigenstate, this eigenstate correlator, and we claim that this eigenstate correlation has a finite contribution only when the eigenstates have this structure. So this component V has finite contribution only when the eigenstates are similar in this region. Similar colors, same colors denote like similar profiles of the eigenstates. Similarly, the other component parameterized by minus L should look like this. And since the full correlator is a product of these two, you obtain a structure like this. So the claim is that this eigenstate correlation has an order 1 contribution only when the eigenstate look like this or belong to this set box L. Otherwise, the eigenstate correlation is effectively 0. So this can be numerically tested by looking at some set of these quartets which have finite contributions, and these are like Z-basis profiles of these eigenstates. A better way to prove this is a better way to corroborate this claim is to count the number of these quartets, which can be done. And this is this is effectively the number of quartets which dominate, which have an order 1 contribution, and we can plot the distribution of all the eigenstate correlators which are sampled from the eigenstates. And scaling this distribution with this counting, we can collapse the distribution. So this kind of corroborates our claim that only these quartets contribute to the eigenstate correlations. And so basically, this is exponentially small in the system size. So we say that only an exponentially small number of these quartets will give you a finite eigenstate correlations. Now we get back to the dynamics of the operator entanglement, which we look at in Fourier space for convenience, because this complex space just becomes a delta function. Now we leverage the fact that only eigenstates belonging to these quartets will dominate the dynamics. So in this regard, we define this quantity, which is an analog of the Fourier space purity, but we only include order 1 contributions from this set. So yeah, so a numerical data for both of these quantities, the original Fourier space purity and this, which only contains contributions from these quartets, is shown in this figure. And as you can see, the data falls on top of itself quite nicely. So this this basically goes to show that if you only account for these dominant quartets, you can account for the entire dynamics of the operator entanglement. And so basically, only an exponential small number of these quartets are actually contributing to the dynamics of the operator entanglement. So what is left here is only this function theta, which is the difference between the quasi-energies or the energies of the time evolution operator. So we surmise that further organization within this set of dominant quartets based on the energy spectrum, based on how these 4 eigenstates are separated or how close they are in the spectrum. This organization might shed further light on the dynamics of the operator entanglement. So we do basically this in the next slide. So we propose this organization where you consider a set box Rx, Ry, where we consider a larger region in which the eigenstates are similar, the region which is larger than the initial central region, and we necessarily require the spins to be different at the interface in these two, in the pairs of eigenstates. So and we define another analogous quantity, which is a part of the Fourier space purity, which only contains quartets from this set. This can summing over all these sets can lead us back to the original Fourier space purity, or the Fourier space purity which only has domination from the dominating quartets, which we just showed that is enough to account for the dynamics. So yeah, we can eventually relate this back, and this quantity has already been studied previously by Vikram and Stitadi. So I'll just use their results. So they show a scaling form for this quantity, which has where another length scale xi emerges, and this length scale scales with this exponentially with this with the distance r, which separates r, which kind of measures the distance in which these eigenstates are the same. So this plugging this back into this equation, we obtain another energy scale which scales like this. So the upshot is that we can exactly do this calculation in certain limiting cases around this energy scale, and doing this summation explicitly by plugging the scaling form into this equation, we obtain this behavior for the Fourier space purity, which exhibits two power law regimes. So initially there is a two power law regimes which are separated by this characteristic energy scale, which is dependent on the cut. And this can be again visualized on the data that we had for the Fourier space purity. Fourier transforming this back into real time, we obtain this relation where the purity shows a very slow decay initially, and after this characteristic energy scale, characteristic time scale, which like energy scale in the Fourier domain, it becomes a time scale. After this characteristic time scale, the decay speeds up. And again, relating this back with the previous surmise that we had for the operator entanglement. Yeah, I'm almost done. Yeah. So we already had a time scale where the a time scale which scaled exponentially with the cut, and which basically leads us to equate these two scales. And so the scale that we already had zeta earlier, which we surmised, is actually emerges from these eigenstate correlations. And so basically, to conclude, we have two regimes in the operator entanglement, which is like initially there is a very small decay of purity, which is a very slow growth of operator entanglement. And after that, after the characteristic time scale, which is parameterized by the cut, you observe the universal logarithmic growth of entanglement in many body localized systems. And since this characteristic time scales exponentially with the cut, that's how we obtain the logarithmic Lightcone. So just to summarize, we looked at the operator entanglement and explained its behavior in terms of eigenstate correlations, which gives a microscopic theory, gives a microscopic understanding of where this logarithmic Lightcone emerges from. So yeah, that was it. Thank you.
So you mentioned that there are an exponentially small number of quartets that contribute for the growth of operator entanglement. Yeah. So what determines which of the quartets are dominantly contributing?
Yeah, so here we use properties of the many body localized phase. So you have a 4-point eigenstate correlator, which actually I think I can just go back to the equations somehow. Yeah, so if you look at the eigenstate correlation here, so it has some eigenstates which are written in a bipartite basis, and there are some arbitrary contractions over these eigenstates. So if you imagine the states to be like completely localized, if they are just Z basis product states, then you can show explicitly that when these eigenstates have this form, exactly this form, so the eigenstate is similar in this part of the subsystem. So alpha and beta are the same in this blue region, and alpha and gamma are same in this green region, and so on, indicated by these colors. Then this eigenstate correlator will be 1, otherwise it will be 0. This you can explicitly show for product states. Now, many body localized states are also localized in some basis, and you can associate them with certain localization centers. Like for the model we used, which has disorder in the Z basis, the disorder couples to the Z basis. So the localization happens in the Z tensor product basis. So every eigenstate of that model will be close to some Z basis product state, which is the localization center of that state. So you can just consider them to be slightly smeared around that point. And then you can basically say that this relation still holds approximately. So this we first surmise, and then we show numerical evidence that this actually holds. Does that answer your question?
Trying to understand one of your claims in the earlier slides. I think the claim, if I understood correctly, the claim was that this new object that you're defining, the operator entanglement entropy, has in it the information about all 4-point OTOCs. Is that correct?
Yeah. So let me just. Yeah. So if you consider a unitary time evolution operator of this form. So my original system has this dimension. Right. So if I take a cut like this through the operator and interpret it as a state and calculate the entanglement between these two regions, so this has information about of all the, you consider local operators in this side of the system and local operators in this side of the system, and you consider all OTOCs that spread from this subsystem to this subsystem, and this is kind of summed over all of this.
I see.
So this has been shown. So this actually happens through the eigenstate correlations, because the eigenstate correlations are related to OTOCs in this manner, which I think Vikram talked about. So there's this paper by Han and all, which they relate this eigenstate correlations with this.
What I was going to ask, do we have some similar understanding for higher OTOCs, higher point OTOCs, say 5.6?
Not that I know of.
Thanks.
I have actually one follow-up and a separate question. You cannot quite invert this relation, can you? If I give you access to these purities for different L and, okay, T will not matter, but different L's, can you invert this relation, do you think?
Invert the relation of
PLT with the OTOCs? Basically, can you extract?
No, this is kind of averaged over.
Averaged over.
This is not invertible.
It's not invertible.
Yeah,
okay,
so
that's fine. And I had another question. Like, what is an experimental probe of MBL? Like, because in any system you won't typically be able to calculate an entropy or these eigenstate correlation.
Right. So this can be in two parts. Like, are you asking for an experimental probe of the many-body localized phase, or the experimental probe of the information spread in the many-body localized?
Of the phase. I don't know whether it's called a phase or not, but of an MBL system. Like, if how will I determine whether it's an ergodic or really speaking? Like,
right. So again, we have the absence of transport, and logarithmic in time growth of bipartite entanglement should be probable. And so this could be kind of a good probe in the sense that you know that ergodic systems at least have a linear Lightcone. So if you like at least measure correlations to look at the profile of information spread, which could serve as a good probe, at least which my understanding is concerned. And I think absence of transport is one good probe, which is very conventional in condensed matter systems. Plus, you can look at not OTOCs, but response functions, which are related to linear response. And yeah. Since they are directly related to transport, the response functions, then I think that is a very conventional probe in condensed matter. So, but I don't know how good it is.
Any further questions? If there is no question, let's thank Ratul for this talk.